The graph of density rho versus absolute temperature T below shows three states 1, 2, 3 of an ideal gas. The mass of the gas is constant. Find the relationship between the pressure P and T when the states change from 1 to 2, 2 to 3, and 3 to 1. For the first case, where the gas changed from state 1 to state 2, this process happened at the temperature 2 T0. So that means the T1 same as a T2, which is equal to T2 T0. The temperature is constant. So that means in this process, it obeys the Boyle's law. According to Boyle's law, the P is inversely proportional to V. So that means from here we know that the P pressure does not depend on the T in the process when the gas changes from the state number 1 to number 2. P does not depend on the T. When the gas now change from state 2 to state 3, the density rho is the same, which is a rho naught. So rho 2 same as rho 3. But we know that given by the equations that the mass of the gas is a constant, so that means it won't change. So that means if the rho 2 same as rho 3 means that the V2 should be same as the V3. That means from here we know that V2 same as V3. Okay, so that means the process when the gas changes from state 2 to state 3 is an isochoric process. Now, if it is isochoric process where the volume constant, so that means this process obeys the pressure law. Okay, so that means the pressure is directly proportional to the temperature T. For the gas now change from state 3 to state 1, we notice that the graph that connecting the state 3 and state 1 is passing through the origins of the graph of rho versus T. So that means this graph we can write mathematically as the rho equal to KT. You compare with the y equal to mx plus c, then we know that this k is the gradient of the graph, rho is the y-axis, and the t is the x-axis. The intercept is equal to 0. So now we can write down rho equal to KT. We name this as equation number 1. But our aim is to know what is the relationship between the pressure and temperature. So to see the relationship of P and the T, now we start from the equation of state, the ideal gas law, PV equal to nRT, and then now we change this number of mole n into m over m, where the small m is the mass of the gas in this case, which is fixed, and the m, capital M, is the molar mass of the gas. Now we move this V volume at the left hand side to the right to get the m over v, and this molar mass we move it to the left hand side of this equality sign, so we have Pm equal to m over v times RT. The reasons of taking this step is because we want to write this m over v in terms of the rho. So now we have this Pm equal to rho RT. Rho is the density of the gas. And now we change the density of the gas rho as a subject of the equality of the equations. So we have rho equal to mp over RT. That means now we can substitute the rho by KT from the equation number 1. So we have the KT equal to PM over RT. And bear in mind that because we want to find the relationship between the pressure and the temperature T, so that means now we change the P, we write the P as a subject of the equations. So we have P equal to K R over M times T squared. So that means the relationship between P and T is this, where the P is directly proportional to the T squared. Now as summary, now we know that when the gas changes from state 1 to state 2, the pressure is not depends on the temperature T. From state 2 to state 3, the pressure P is directly proportional to the temperature T. While from state 3 to state 1, the pressure P is directly proportional to the T square. That means the temperature square.